Okay, so now we're going to be doing chapter 9, which is we'll be discussing correlation and regression. Correlation exists between two variables when one of them is related to the other one in some way. For example, the number of hours studied for an exam may be related to the grade on the exam. So there might be a correlation there. So we would investigate whether there's a correlation between number of hours studied and your grade. To find correlation, we can use a scatter plot, and that's a graph in which the paired samples are plotted on the Cartesian coordinate plane that you're used to, the XY coordinate plane, where X is our independent variable and Y is our dependent variable. So we may, in our example, put the hours studied on the X axis and the person's grade on the y-axis, and we could plot the points, and if it looks like they are sort of a straight line, then we would say they are linearly correlated. But we can look at other types of relationships also. In Minitab, we will go to Graph, Scatter Plot, and choose the option Simple. Enter in your X values into column 1, enter in your Y values into column 2, and then graph and see what your graph looks like. Pearson product moment correlation coefficient is a value that measures the strength of the linear relationship. It is also not called the linear correlation coefficient. It's denoted by a lowercase r, and it measures the strength of this linear association. Now notice, if you have a strong relationship that is not linear, suppose you have a parabolic relationship or a logarithmic relationship or an exponential relationship, you may have very strong relationships between x and y that are not linear. And r, the linear correlation coefficient, measures the strength of only the linear association. It estimates rho, the population parameter, or the population correlation of this linear association. So R is our sample correlation coefficient, and rho is the population correlation coefficient. So think about this for a second. The Pearson coefficient measures the strength of an association between x and y quantitative values in the sample. Do you think the answer to this is yes or no? Take a minute. Think about what we've just been talking about. No, because the Pearson coefficient only measures a linear relationship or a linear association. So there may be very strong relationships between x and y that are not linear, and the Pearson coefficient only measures a linear relationship. In interpreting R will always be a number between -1 and 1 inclusive. An R that is close to 0 signifies that there is no or very weak linear correlation between x and y. As R gets closer and closer to 1 and -1, we conclude that there is a significant linear correlation between x and y. If R is exactly equal to 1, then we say that there is a perfect positive linear correlation between x and y. And if R is equal to -1, we say that R has got a perfect negative linear relationship. A negative linear relationship, if you remember from your reading that was assigned for this chapter, it would mean that as x increases, y is decreasing. But how close is close enough, right? So we're going to look at correlation and compute the correlation coefficient using Minitab. You're going to go to Stat, Basic Statistics, and then Correlation. Then it will give you the correlation coefficient as a number between -1 and 1 inclusive. But what you can really see is it close enough to 1 or -1. You can look at the computed p-value. If that is less than or equal to the significance level, then we conclude that there is a significant linear correlation. Recall from our work in chapter 7 and 8 with hypothesis testing, normally a p-value less than or equal to 0.05 is considered significant, and thus a p-value that is less than or equal to 0.05, we would conclude that the linear correlation or the linear relationship between x and y is significant. Otherwise, we would state that there is not enough evidence to support a significant linear correlation. Some other ideas on the correlation coefficient are, first, the value of r does not change if we convert our values to a different scale. For example, height could be in centimeters, meters, inches, feet, kilometers, etc. And regardless, we would get the same value of r. The value of r is not affected by the choice of x and y. Okay, so if x is linearly related to y, then y is linearly related to x. So if we interchange x and y, r remains unchanged. R squared is the proportion of the variation in y that is explained by the linear association between x and y. Here's an example to explain how r squared can be analyzed. Suppose we have as our independent variable x the number of beers, that is the amount of beer that is drunk, and that y be the blood alcohol level. Now, an r squared of 0.72 would say that about 72% of your blood alcohol level is explained by the amount of beer that was drunk. That means there is another 28% of your blood alcohol level that is explained by other things. For example, it could be your body's metabolism. It could be your body's mass, your weight. Okay, so an r squared measures the proportion of the variation in y that is explained by the linear association. And it is actually the value correlation coefficient r actually squared. So true or false, if r equals 0, then x and y have no correlation. Think about that for a minute. What do you think? That answer is false because r is only talking about a linear relationship. So if r equals 0, that means there is no linear relationship, but there may be a very strong relationship, just not a linear one. True or false, if x and y have a strong linear correlation, then likely x causes y or y causes x. What do you think about this one? Stop for a second and think. This answer is false. This is a very, very common mistake. Just because there is a strong linear relationship does not mean that one is causing the other. All right, so here are some common errors involving correlation. Correlation does not imply causality. And averages suppress the individual variation. We saw this when we were looking at chapter 6. And it will inflate the correlation coefficient. So use care when your data that you are inputting is based on averages. And remember, there may be very strong correlations other than linear correlation. Now, the next concept we're looking at is regression lines. Given a collection of paired sample data, x and y, where x is going to be our independent variable and y is our dependent variable, we can come up with the regression equation. Y hat equals b naught plus b sub 1 x. This should look very familiar to you, as this is in high school. When you studied equations of lines, you probably learned y equals mx plus b. Well, in this case, b1 is that slope and b naught is the y-intercept, just like you learned when you were in high school. Now, this describes the relationship between x and y. This graph is called the regression line, or sometimes known as the line of best fit, or the least squares line. The reason for this you can get from your reading in the book to see why the regression line is also known as the line of best fit. Now, x is our independent variable, which is also sometimes known as the predictor variable or the explanatory variable, and y is our dependent or response variable. So in regression, we have two sample statistics, B0 and B1. These estimate the population parameters beta0 and beta1 respectively. Okay, so B0 is our y-intercept. It is equivalent to the expected value when the independent variable x is 0, and B1 is our slope or our rate of change in our sample data, where beta0 and beta1 are what we expect in the population. Similarly, y hat equals b sub 0 plus b1x estimates y equal to beta0 plus beta1x. This y hat is from our sample statistics, and the beta y equals beta0 and beta1. These are our population parameters. This is what is in actuality, and this is what we're seeing from our sample. In using regression, now we can only use regression lines for predictions if there's a significant linear correlation. Minitab will find you a regression equation for any paired data that you put in. But if you have not taken the time to analyze for the correlation or the linear relationship, if you find when you do correlation analysis that there is not a strong linear relationship between x and y, then the regression line that you find, the equation for the regression line, will not be a good model for our data, because the regression line is a model for a linear relationship. If there is not a significant linear relationship, then there is no point in finding an equation for the regression line. All right, so if it turns out that we do not have a significant linear correlation, then the very best predicted y value or dependent variable or response variable is the sample mean. If there is a significant linear relationship, then we could substitute in an x value into this equation to estimate a y value. This is known as the predicted value when we input a particular predictor variable x. Right? Now notice, but we need to stay within the scope of the available sample data in which that regression line was modeled after. If we try to predict outside of the sample data used to come up with that model, we will not be getting good predictions. The marginal change. The marginal change is the same thing as the slope. It's the rate of change of y when x is increased by 1 unit. That is the same definition that you learned in high school for the slope of the line. We can do regression analysis on Minitab. You go to Stat, then Regression, and then Regression again. Your responses are your y values, and your predictor is your x values, which you have put into column 1 and column 2, or into columns in your worksheet in Minitab. You go to Options and you say Fit Intercept, and when you click on the results bar, you will get the regression equation, you will get S, and you will get R squared, S being the standard error of the regression line. All of this will be given to you. You'll be given a lot of different information, and some of it we will be using in the class, but all of it is explained in your reading of chapter 9. Now we can do Minitab to graph the regression line. You go to Stat, Regression, Fitted Line Plot, and your response is your y values, and your predictor is still your x values. And select Linear Model, and you will get the graph of the paired data. If the paired data looks fairly linear, then we would say that that's we have a linear relationship, and we can see the line of best fit, also known as the regression line, on this graph. Now, variation for a point. You can see some illustrations of this in your textbook, but the total variation is the distance from the mean, each y value from the mean of the y's. That's known as the total variation from the mean of the point xy. It's the vertical distance from y to the mean of the y values. Explained variation is the predicted value of y, the y hat, minus the mean. Now remember, whenever you're doing the regression line, they are all the points on the regression line are x, the predictor variable, and your predicted value for y, or your y hat. So the difference between the y hat and the actual sample, the actual mean of the y values, is known as the explained variation. And the unexplained variation is the distance from the actual value y to the predicted value y. Okay, so it is the vertical distance from the point xy, which is from our sample, to the regression line point, which is x y hat. The distance between these two values, this y and this y hat, is known as the unexplained variation. So the variation for a sample, we have the total variation, which is you sum up, you find each of the y minus the average of the y's, square those values and sum them up, and you will get the total variation. The total explained variation is you square each of these values and sum them, and for the unexplained variation, you do the value y minus the predicted value, y hat. Square those values, sum them up, and you will get the unexplained variation for the entire model. Note, total variation is the sum of the explained and the unexplained variation. This total variation is equal to this value plus this value. Now the variation for a sample in Minitab, the total variation is known as the total SS. You will see you'll get a lot of information when you go to regression in Minitab, and if you're asked what is the total variation, look for the value total SS. If you're looking for asked to find the explained variation, you go to regression SS, which is in a table. And you can see the Minitab output in your Minitab lab before you even do the lab itself. Look in your lab book and you'll see an example of where all of these things are found. And the unexplained variation is found under residual error SS. So you can find the total variation, the regression, the unexplained variation, and the explained variation all inside of the information that Minitab gives you. The coefficient of determination is also given by Minitab, but the R squared, we talked about this a minute ago, it's the amount of variation in y that is explained by the regression line. It's equal to the explained variation divided by the total variation. And so you don't necessarily need to use this formula because Minitab will tell you what R squared is. The standard error of the estimate, S sub E, is equal to this formula here, but Minitab also gives it to you, but it is the measure of the differences between the observed sample y values and the predicted values that are obtained using this regression line. Remember, y hat are the predicted values predicted by this regression line. All right, note, Minitab calculates both for you, R squared and S. So you don't need to use those formulas by hand. I just wanted to show you where they came from. Okay, so now we also might want to come up with a prediction interval. And in Minitab, you go to Stat, Regression. Under Options box, enter the values for X in the box labeled Prediction Intervals for New Observations. And it will give you, and enter the desired confidence level, and it will give you a confidence interval for these predicted values for X values. You'll see a little more of this. You can read about it in your Chapter 9 reading. You'll see a little more of it in Lab 10. And remember, go to your Minitab lab book before the lab to read some of these examples on how to find all these things. All right, so that's the end of chapter 9, where we looked at correlation analysis and regression analysis. And it's time now to go try some problems.